it is time to introduce velocity. Okay, there are all kinds of motion in the world. If we can start from something simple, why do we start from something more complicated? So let's start from the simplest kind of motion. That's motion along a straight line. Okay, among all the motions along a straight line, a motion with a constant velocity is the simplest. So that's where we start. We're going to look at displacement. So that's the first thing we're going to introduce in this part. The second part is definition of an average velocity. And then we're going to look at different examples of motion along a straight line with constant velocity. Okay, motion along a straight line. We here have a line with an arrow that represents our coordinate system. Coordinate system does not grow from the ground or grow on the tree or fall from the tree. You never bump into a coordinate system with your nose. So they are what we created in our minds. That is used as a reference to keep track of a motion. For example, in this case, a smiley face. So smiley face is placed on this reference system. Reference system is imaginary, and you can always make your own reference system. As a matter of fact, you do need to make your own reference system. See, this reference system has an arrow that points to the right, meaning to the right is positive, to the left is negative. It's one-dimensional because it's a straight line. Okay, so here, the smiley face moves from 0 meter to 200 meters. And in that case, the position goes from 0 to 200 meters. Displacement is final minus initial position, that equals to 200 meters. So this is displacement. Has to do with the initial and the final positions, does not depend on the exact path. Next, we're going to introduce what's called average velocity. Okay, we're going to introduce what is average velocity, and also we're going to tell you what's not average velocity. We want you to learn about average velocity as we introduce here. We want you to unlearn what you might automatically assume what average velocity means. So this is what we're trying to do. Here, we do define average velocity as displacement divided by time. Okay, average velocity equals to displacement divided by time. Then you say like, why don't you say v equals to delta x over t? Yes, that is fine too. I'm just reminding you, as I give you a heads up for, as we give you a shout out for, as we alerted you, these symbols are used to represent different properties. Symbol and property are equivalent. Delta x is equivalent to displacement, delta t is equivalent to time, and v average is equivalent to average velocity. So these are just two different ways to represent them. To use these symbols makes our equation looks easier and simple, easy to see. And why would somebody think average velocity is this? Well, maybe sometimes I do think average velocity is the velocity of the first piece of motion plus the velocity of the second piece of the motion plus the velocity of the second portion of the motion, added up and divided by 3. Average, right? So we know a lot about average. Like we know so much about average. Like average age is total age divided by the number of people. Average gas price is total gas price divided by the number of stations. Why do we do that? I don't know. But anyway, we know a lot about average. And inevitably, we're gonna extend our knowledge and assume that average velocity is the average of velocity values in different portions of the motion. But remember, that is wrong. Please don't do this. If you automatically do that, that's wrong because, like, sorry, you don't get to invent that. That's already invented. Okay, you're born a little too late, sorry. We need to stick to the definition here. Average velocity is displacement over time. Okay, this one almost looks correct, right? But it's wrong. Okay, so your job is to learn the correct thing and apply the correct knowledge and unlearn what you automatically assumes it. Let's look at an example. Okay, evaluate the 2 calculations, which is correct. Car travels up a hill at a speed of 40 kilometers per hour. Well, did we say we always use SI base unit? Well, in this case, we're not. So this is when we actually need unit conversion. In this particular case, it returns downhill faster, right? 60 kilometers per hour. Calculate the average velocity of the trip. Okay, can we add them up and divide it by 2? Well, actually, somebody should have written the parenthesis. If you write the parenthesis, that's 50 kilometers per hour. Is that right? Or should it be 0? And you say like, oh, how can velocity be 0? You're going at 40 and 60 and average should be 50. Why should it be 0? Okay, that's because according to our definition, average velocity is displacement divided by time. What's the displacement? If a car travels up and returns to the original position. Final position, initial position are the same, so displacement is 0, and therefore the average velocity by our definition is 0. And if you might think it's a 50, that is okay up to now. So from today on, do not do the add up and divide. You have to unlearn that. Your job now is unlearn that. So the average velocity, there's only one correct way to do it. That's displacement divided by time. Okay, so let's take a look. For one-dimensional motion with a constant velocity, remember this is the simplest of one-dimensional motion? Okay, there are 3 variables, 3 properties to describe this motion, to characterize this motion, to make clear about this motion. Okay, so what are they? Delta x represent displacement. V represent what? Velocity? Yes, that's correct. Delta t represent what? Did you say time? Absolutely, great job. So these are the 3 properties that characterize a one-dimensional motion with a constant velocity. Okay, and how are they related? Physics is about finding out how different properties are related. So the velocity equals to displacement over time. Remember, it's a constant velocity, okay? So on top, this is the condition where you can apply this relationship. If it's not a constant velocity, then you cannot apply this. Does that make sense? You can apply this relationship only when it is a constant velocity. So that is this. And on the right-hand side, we're going to leave that blank. We're going to fill it in later. So this is what you know about a one-dimensional motion with a constant velocity. Then you might be wondering, hey, we're sitting here or standing here or walking around here to learn about the motion along the straight line. What about all those motions in the world that are not along a straight line? So physics is so restricted. We're just studying something that almost doesn't exist. How many cars actually go exactly in a straight line? Okay, you're right about that. So what we do is actually we keep our models simple, okay? When the motion is not exactly in a straight line, we simplify it. Okay, for example, here's a dog, and the dog does not go exactly in a straight line. Okay, but we simplify it. We want to know the essence about the motion. That is, so let's say Dennis actually walks along a straight line. Let's see, Dennis is perfect. Dennis walks along a straight line as the owner of the dog. And Dennis goes from 0 meter position to 20 meter position, and the dog starts from the same point and ended at the same point. Whoops, is the dog leashed? I don't know, but anyway, the dog looks pretty happy, so let's not worry about that right now. So the displacement is final position minus initial position, that's 20 meters. Average velocity is the displacement over time, 200 meters divided by 400 seconds, that's 0.5 meters per second. Did somebody measure the time? Well, obviously, I think somebody did measure the time, and the time is 40 seconds. Well, somebody did a measurement of the time. So if somebody does measure the time, that's 400 seconds, 0.5 meters per second. So you can see when a motion is not exactly in a straight line, that can be simplified. So this way, we keep our models in physics very simple. Would you like to look at another example? If you don't mind, here. Okay, if a lacrosse player player is the word. If a lacrosse player can fly 14 meters per second horizontally, a lacrosse player can fly. Yes, can he reach a lacrosse ball 30 meters away in 2 seconds? We're assuming that ball stays there. Okay, all right. Let's say, let's translate. This is how we solve problems. If it's a word problem, we need to translate the words into equations, because what we know, what we learned is equation, right? So the question is in words. You always have to bridge between what you know and what you don't know. What we know is that, let me show you what we know. Displacement, time, and velocity are related this way. Okay, so here, all right, here, let's see. Translate. Displacement is 30 meters. How do we know 30 meters is displacement? Because it says 30 meters away. That implies it's a displacement. It's the change of position. Velocity is 14 meters per second. Did this say 14 meters per second is velocity? No, it didn't. Now, how do we know it's a velocity? Well, here is a hint. Meters per second. Meters per second is a unit for what? For velocity. Yes, it's a unit for velocity. So we translate that. We use that clue, that hint, and translate it back to velocity. So we're doing translations here. So the translation we're doing here has a fancy name. It's called the problem analysis. Analyze a problem. Okay, so here's what we know. They're related. Time multiplied by the velocity equals to displacement. So we're assuming the lacrosse player moves at a constant velocity. Why do we assume that way? Because that's the only way we can solve a problem. Remember, simplify. Okay. Unless it says otherwise, we can assume in this case it's constant velocity. Okay, so this is the equation. Remember, we do not use arithmetic, we use algebra. Set of equation, time times 14 is the velocity equals to the displacement. These are all SI base units. Meters SI base unit. Meters per second is SI base unit. So that's why I can plug the numbers directly into the equation. What if they're not? If they are not, convert the units first. Okay, so if we solve the equation, T equals to 30 divided by 14. That's larger than 2.0 if you do a calculation. So here, the lacrosse player actually needs more than 2 seconds to reach the lacrosse ball. So 2 seconds is not enough. That's how we evaluate. Evaluate is to use facts and numbers to draw conclusions. And our conclusion is, no, he cannot reach the ball. In summary, for velocity, we learned 3 things. Number 1 is motion along a straight line with constant velocity. This is a simple model of motion, and it's the simplest of all motions. And please remember, this is the first type of motion we learn in this course. It's the simplest of all. Number 2, we learned the definition of average velocity. And remember, you have to unlearn what you might naturally use as an average velocity. And that is important. I'm counting on you to do that correctly. Number 3, we went through 2 examples to learn about that. So this is what we know about velocity.